Hello, this is Team The Erudition. So we built Forge, which is a competitive benchmarking platform for matching engines, in which the contestants can submit their code in three primary languages, which is basically C++, Rust, or Golang. And obviously, because the contestant is submitting a matching engine, so we need to test the correctness of it, how well it is able to handle a large number of orders. So basically, load test it and verify its scalability and overall design. So to do that, we had to spawn thousands of trading bots and obviously score them based on their performance. So initially, what we had done was like in the first 3 or 4 days, we had set up a thread-based concurrency system where we had used Golang subroutines to essentially navigate or utilize all our services. But what was happening was, or the conclusion which we came to with that system was that because it is primarily running in threads at the end of the day, when we increase the scale of the system and increase the amount of submissions or the trading bots, eventually it would just fall out and it won't be like viable. So we had to switch to an event-driven architecture, which was essentially our Redis publish and subscribe backbone. Now here we set up a microservice architecture, a proper microservice system where all the services were individual containers which are running and publishing and subscribing to the various Redis channels. And there were two things which were problematic in this system as well. One was that the system was not automatically meeting the needs of like the number of bots were not increasing and decreasing as per the needs of the system at that moment. And it wasn't as such being replicable, like wasn't able to replicate the services. So this was solved by our third version of our system, which in which we use Kubernetes, which like obviously solved both of these problems. So we'll get to the demo now. So I'll just walk you through a submission. So it is already logged in, but obviously the contestant will log in and they'll get an API key with which they can submit. We kept an API key now because we wanted to allow CLI submissions as well, and eventually a way to submit through GitHub as well. Now the contestant can select the code, choose a file as well. 1 second, I'll just get the file as well. Yeah. So we had like tons of versions of matching engines which we were using, but for now I'll show you the correct one because we already tested the wrong ones just before this. So I'll just upload and build. Now, once I click on the upload and build button, what happens is it passes through our first service, which is our API service. Now, the API service does three main things. The first thing it does is it extracts the contents of the file which we have submitted. Now, we obviously kept into consideration the fact that the contestants can submit zips or tar files as well. So we had kept an extraction system. And obviously, to prevent contestants for like spamming our system with submissions, or maybe they didn't have net and then it spams the system with several submissions. So we had to keep a rate limiting system as well. So we kept a bucket based token rate limiting. Now, once it gets extracted, what happens is it passes through our second service, which is our build service. Now, the build service is basically responsible to convert all the extracted code into a shared object file. And once it does this, it publishes it to engine build. Now, once the engine is ready, what it does is it spawns and run a container, which is responsible for making the various functions which are present in the matching engine available to the external API. So like it converts it into HTTPS, and we did that through a C application bridge interface. Now Rishit will explain the overall bot fleet controller and the workers.
So now, talking about bot fleet. So once the contestants matching engine gets compiled, deployed, and it basically passes all the health checks, we emit a Redis event, which is Forge engine ready, and that's what starts the bot fleet. So our bot fleet is a controller worker architecture which runs over gRPC. So there's one controller sitting and listening to these Redis events, and the moment it gets one event, it generates a test configuration and starts distributing works across a bunch of workers. So now the connection between the controller and the worker is actually a bidirectional gRPC stream. We use the same stream for pretty much everything, like the worker registration, commands from the controller, and the liveness tracking. So when the worker comes up, it registers itself and then it starts sending a heartbeat every 5 seconds. It's just the worker ID and the timestamp which makes up the heartbeat. And the controller treats that as the liveness signal. So if the stream drops, the worker is considered dead and it is removed from the pool. So now coming on to the traffic generation part, because we did not want to just send orders at a fixed rate, because real markets do not behave like that. They are unpredictable and random. So what we do is we use a three-state model, which consists of calm, elevated, and burst states. So every state has its own poison lambda, which controls how aggressive the market would be at a particular time. So to switch between those states, we are using a 3 cross 3 Markov transition matrix. So for every 10 orders, we would roll the matrix across every state, and it decides if we should stay in a particular state or we should move it to somewhere else. So let's say if we are in a calm state, for example, it would decide that 70% of the time we would stay in the calm state, 20% time in the elevated, and 10% time into the burst state. So that makes the events more natural looking, and it simulates real market conditions too. Uh, on top of that, we randomize the order types too. So there are six different order types, which are limit buys, limit sells, market buys, market sells, cancel best, and cancel random depth. So for this randomization, we are again using a Markov chain, which is a 6 cross 6 transition matrix. Now, coming on to the reproducibility part. So, for every test, we have a global PRNG seed. So, every worker derives its own seed from the global one. And this ensures that there is a repeatable randomness of order sequences, timing decisions, and behaviors, which makes the debugging easier. And it also ensures that there is fairness for all types of submissions. And finally, all the telemetry gets streamed out. So every schedule timestamps, send timestamps, receive timestamps, and also the latency measurements. Everything goes into the Red Panda and it gets processed by a telemetry service and it gets handed over to Oracle. So that's what is our bot fleet all about. Now Tejas would continue ahead.
Yeah. So now that we understood the bot fleet workers and the controller itself, the core thing which is left is obviously to identify how to actually score the matching engine. Now, the first and foremost thing which should be checked in a matching engine is its correctness. Now, to be able to identify correctness of a matching engine, we need a reference engine as well. So this leads us to our another service, which is our Oracle service. Now, the Oracle service is responsible for auditing the matching engine's correctness against our own reference order book implementation. Now, what happened was initially what we had done was we had set up a asynchronous matching and filling. So what was happening was that the filling in the contestants matching engine was happening before the contestant before our own matching engine, which led to like incoherent submissions and filling, which was undesired. So we had to set up a synchronous matching engine. Like we had to remove the Golang routine in that. And basically, what we did was um, we started doing it synchronously and measuring three things. First was the fill accuracy itself. And the other thing which we checked was the price time priority. So we had to check if the fills are in the correct order and the total match fills are respecting the price time priority or not. And the third thing which we were checking was that if the scores are getting accumulated, they should not get reset between test cycles, because in between what was happening was that the scores were coming and they were getting reset immediately, which was leading to a zero fill accuracy for some like quite a long time, in fact. So after that, what happens is once the Oracle computes the matching accuracy and the correctness and the price time priority, it will publish the results to our last service, not our last service, but like the visible part, which is our leaderboard. Now the leaderboard will compute the overall score of the entire matching engine submitted, which we based off like four things. First was your transactions per second. This was about 25% of the total score, and we had kept 20, 10, and 5% to the 50th and 90th and 99th percentile latency. And the last thing, which is obviously the most important, 40% was given to the fill accuracy. We had also kept an error penalty as well, because some matching engines were actually performing really well, but there were tons of errors in them. So we had kept like a 8%, I guess, error penalty as well. Now, because the amount of metrics which are coming out were like a lot through red pandas, we had to keep a buffer as well. So every 2 seconds, what we were doing is we were aggregating those metrics and then feeding it to our leaderboard. Now, I'll just show you what happened in our submission. So we submitted as the edition. To just explain what is the leaderboard's scenario right now. We had like 8 types of matching engines which we tested. So with the one which we tested was obviously the decently correct one. And the others which we tested were buy only. One was inverted price time priority, and the last one was it was not doing anything. It was like an unreactive matching engine of sorts. So this got scored based on all the metrics and the transactions per second. Now, this gets streamed actually, but because I showed it to you now, it's not getting streamed when it's static right now. But this was like the score, and you can check how many orders got audited and how many errors there were. Now, apart from this, I'll just show you another thing, which is two factors which we had, like other services which we had kept for like observability and metrics. Now, so obviously, since this is a distributed system, one thing which we need is to be able to trace what was happening and when, and what part of the system is actually causing that error, right? So, like till around 70% of our project completion, what we had done was set up a logging system which was not centralized. And what we had to do to debug was essentially check those logs again and again. Obviously, now that is like anti like counter intuitive. So we set up like a trace parent in our entire system, and it we are observing it through Jaeger, which is an open source traceability thing. Now it just we see that there were an API submissions get, and the UI is a bit bad, but you can just see what requests were done, and you can also see how many milliseconds each request took. So like 10 minutes ago, I submitted all these things. So you can check like what part of the system was corrupted and maybe how much time is it taking, etc. And one more thing to show is the Grafana dashboard. Now, Grafana is obviously a metrics visualizer, like a professional one. So to be able to show these metrics, like you see the leaderboard over here and all the like the factors like the HTTP request rate, the build durations, the engine ready count, etc. To be able to show this, we had to use Prometheus for metric ingestion. So all the services which we mentioned earlier, we had to keep an export stream as well for Prometheus to ingest all those metrics. So I think that concludes all our things. Thank you.